Okay, so again, it's very important you saw, every time I wanted to take data, I pushed the syringe in and let it expand. What's that volume? Pull the syringe out and let it contract. What's that volume? The true volume will be the average of those two. That's the volume if there was no friction. All right, here's some data. So our freezer is about -20 degrees Celsius. So I just said it was like 20 point whatever, who cares? I set the volume to 40, and then I immersed it in freezing water, and I stirred it around, and it did expand a little bit. I heated up the water. I could not get the water up to boiling. It got up to 90 degrees. And so that was the volume of the syringe, and we get a graph that's a line, but it's not a direct proportion, because the line does not go through the origin unless we define a new temperature scale so that the line will go through the origin. Okay, so what I do is I have the students solve for the lowest temperature possible. That is the temperature where the volume of the gas would reduce to 0. Here is the regression equation, not y but volume, equals slope t plus intercept. Find the temperature that makes the gas have 0 volume. We set V equals 0. V is 0, solve for T, subtract over, divide, and you get about -270. And the closer that is to -273, the better your students did at the lab. That is the lowest possible temperature. That is absolute 0. Here's another way. I give my students a graph that goes from -400 degrees Celsius up to 100 degrees Celsius. They plot their points, and it goes from 0 volume to 60 milliliters volume. They plot their points, and they draw a best fit line, and they just extend that line all the way back to where it reaches the axis. And if they do it correctly, it should hit at -273. Try it with your students. I think it's a really good lab. All right, next time we're going to talk about representing thermodynamic processes, and we're going to talk about a project that I do that combines fluid and thermo. Last module, so here we go.